Okay. Tell me when you want me to open the webinar. Okay. Just let me know. Can I open the webinar? Wait. Okay. Can you
Yes,
move? You have.
ready.
Okay. Perfect.
Yeah,
I'll be here in backstage if you need anything.
great to know. Thank you.
Yeah.
Okay. So we are at the top of the hour, and I understand that we can start now. I got a green light. Hello, everybody out there joining us. This is really exciting 2 weeks actually with workshop and with all the seminars and all the information. That is one part that we are contributing today. And to this end, let me go into screen sharing so that we get some virtual imagery underneath. Okay, here we go. Now, first, let me introduce myself. My name is Peter Baumann. I'm on the one hand chasing students at Constructor University through computer science, doing their databases, web services, and software engineering. So you see the more practical stuff. And with the stuff that we have created in research, we have also done a spin-off company, Rasterman GmbH, as it's called in Germany. And this spin-off company is flying in close formation. We are working together, often in the same project, actually, when it fits, so that we also can give commercial support to what we have done. I will show you that a little bit, but this is not the central theme, actually. First of all, I would like to thank the organizers for having me and for finding it interesting enough so that I can now present some ideas and the status of it. The first status is that I'm trying to capture my mouse. Yo, here it is. Okay, so the topic will center around the idea of Datacubes, the notion cubes for spatio-temporal data. And as the title already said, I want to introduce to you EarthServer, the Datacube Federation, and the underlying platform technology Rasterman, just briefly. Talking about Federation, I will demonstrate you what Federation means to us. And then actually, I would like to get hands-on, and that is something that you can follow and recapitulate. I will show you a few things, and most of them you can actually also run in your browser without installing anything, just with a vanilla browser. And many of the demonstrations you will see, actually you will be able to modify yourself and to play with it. And I would very much invite you to do so. Okay, so let's see. Actually, when we talk about ocean data, to me as a computer scientist, and I'm now saying something really stupid because I'm a computer scientist and not a earth scientist, to me, atmosphere and ocean are similarly fascinating in that they offer high dimensional data, not just one dimensional time series and two-dimensional images, but we have 3D, and if we add time, then we have 4D actually. And we have both models that generate data, and we have observations that capture data. We actually have many different let us say, layers. So from surface and actually the connection to atmosphere, deep water, seafloor, subsea floor, when we go into the realm of geology, we have interactions between ocean and other entities, let me say, like atmosphere, but also with the coast. And then we have anthropogenic impact. And we have many different sciences. So from a data perspective, this is something extremely exciting. Now, it is naturally dimensional. And this is where data cubes actually come in. They are a view on data that is just natural for humans. It's human-centric. Because you and I, if we talk about the water, you don't think about thousands of netcdf files, do you? Rather, you think about XY at the surface, and then you go Z negative down into the ocean. So you have 3D, then you add time, you have 4D. So for us, this is just a natural view on data. I'm not saying that data necessarily have to be reorganized for that. Not necessarily. But it's a view on top of the data which complements existing services and makes multidimensional spatiotemporal data better to handle. Why that? Well, first of all, the huge number is reduced to something we can oversee. So instead of millions of products like the satellite people are proud of, we have for each sensor, for example, one object. That object can have 1, 2, 3, 4, 5, 6 dimensions, whatever. And like with seamless maps, where we can walk without boundaries, without limits in latitude, longitude, here we can walk in height and depth and a long time. And the analysis of long time series is a killer application today. And once we have this paradigm, actually, we can build powerful services on top of that, which make our life a little bit easier and also allow people to participate and use the data that are not necessarily experts in all sorts of computing technologies, but hey, they just want to use it. A little bit like my mobile phone. I don't really know how modern mobile phones work internally, but I can use it. Good. This gets me to the work that we have done in our research in computer science that centers around our rasterman system. That stands for Raster Data Manager. And it's an engine that allows to query n-dimensional data cubes. As simple as that. Actually, without us knowing at that time way back, we have pioneered that. Meantime, data cubes are known, so I don't need to explain that so much. It was just one slide. That is also documented. And so in the end, it's a little bit like a database system. It does management of data and analytics, just not on tables, but on data cubes. This is not just something on top of X-array like some tools do it, but actually it's a full stack implementation from top to bottom, employing parallelization, federation, there is appropriate security, and everything is based on standards. It's scalable. We have run it on a nanosat in space. Yes, Rasterman has been in orbit over laptop cloud to the heterogeneous federations. And what we have built in is also green computing by minimizing the energy consumption for processing data. It is the standards blueprint, for example, for the ISO SQL Part 15 MDA for multidimensional arrays. And yes, I admit we are proud of that, that SQL people found it interesting enough to adopt our Datacube query language as a part of SQL. And there's a similar language. It just looks a little bit different from its flavor, from its syntax. In OGC ISO, there it's called WCPS for Web Coverage Processing Service. That is the one we are going to look at today because MDA is domain neutral. You can also model human brain images. But WCPS knows about the space-time semantics, which obviously is what we want when it comes to ocean data. Okay, and as some add-on, what we are currently doing in research, one of the things that keep us awake at night is we want to bring machine learning into the Datacube engine. Why that? Well, following the big data principle, ship code to the data. So do the inference on the big data close to them, and you will have to transport less data and you will be faster. Okay. On the right-hand side, you see an example of what we have done with a model trained on crop analysis. And that is the result of a database query, actually using that WCPS language. Without going into too much detail, we will look at it in more detail later. You can see a blue part that is corresponding to the OGC standard. And inside that, you find a function predict, which actually takes as input some area, say Sentinel-2 region of interest. It takes a particular model. In this case, it's about crop detection. And then internally, the server passes that to PyTorch. PyTorch does its magic and returns the classification result, which then can be processed further. One advantage that we believe exists there is, hey, now we have integrated the silos. You don't need to do that any longer separately. I mean, classical analytical formulations, and on the other hand, machine learning. No, it's actually all seamlessly integrated. For the user, it's just another function that is invoked. And so everything gets combined and gets easier for those who write such queries. An additional advantage is that this is integrated with all the mechanisms inside the server engine, where we can do query optimization, we can do distributed processing, data fusion, etc. And the model doesn't get more complicated. The model doesn't even know that. The engine does it and feeds the model with what it understands. So behind the hood, we gain quite a few extra benefits from the combination. Okay, now this sounds very technical, I know. And so for sure you have started thinking now, oops, do I need to learn a new language? Well, not necessarily. Actually, thanks to the strict use of open standards, actually you can use a lot of third-party clients. So can be simple map navigation with open layers, a virtual globe, NASA Worldwind, we will use that today, QGIS, ArcGIS, or to do high-end analytics with Python and with R. So all the different users can come simultaneously and stay in their individual comfort zone. This is how we believe it gets one step simpler to access such data in the form of Datacubes. Okay, now just for the fun of it, a few applications of what we have done. I told you that the query language as such is domain agnostic. And so we have done, for example, with St. Petersburg Polytechnic, gene expression analysis. These are Drosophila embryos, fruit fly embryos, and their analysis over time gives time series. Then human brain imaging, where we got images that again are multidimensional. So humans have been put in a tomograph, and while they got a task to do, like what is the square root of 82, a lot of things were measured. And on these multidimensional measurements, later on, you can do statistics. Getting bigger, PlanetServer is a service that has data about Moon and Mars, and is planning to do Vesta as well. Going even bigger, with Chineka, we have done long back already cosmological simulations. So you see a few megaparsec of universe here and galaxies. And something that I have kept for the last one, because this is something that is always particular fun to me. I said already, we have brought Rasterman into space on this CubeSat, a 3 unique CubeSat in the Orbitans project. We have brought it up there, and OBSAT is still up there. The camera captures images. They are stored locally. And then questions, that is queries, can be sent from Earth into space to this satellite. And the queries get processed on board on the Datacube, and the result comes back. So quite a few things, but not all of that is relevant to us. Now, the Datacube part, I believe, is something that we don't need to discuss so much. Federation is a hot buzzword that is going around. And I would like to actually show you what we do with that. And that is one demonstration. I'm now trying to find out where my window is. Ha, here it is. Okay. And here we go. So let's take an example. This is something that the climate modelers have given me. On the left-hand side, you see such a WCPS query. It is quite involved. The climate modelers told me it determines heavy rainfall risk areas on Earth. Okay. What I can see is that we combine precipitation data with Landsat 8 data. So we do data fusion. Let's send that to Code.de, the German Sentinel hub, and see what happens. So at some time we get a result. Hooray. It utilizes NASA Whirlwind to show these heavy rainfall risk areas. But the more important, interesting thing is happening behind the scene, because here actually we can follow the query path. So this is approximately where I am sitting, and the query goes down to close to Frankfurt, where the Code.de servers sit. And this Rasterman server actually discovers, oops, I don't have all data. I cannot answer this query. But fortunately, I have a friend over there in Warsaw, and this Rasterman server has the missing data. So a subquery was generated automatically, was sent over to Cloudflare, which is the company there. It was answered there. The response came back. It got integrated, and we saw the final result here. I can send the same query to Cloudflare. Now, they in turn have the problem that they must ask back with Code.de to generate the same result. So this is what we have in mind. We talk about location transparent federation. All those instances are completely autonomous, but they collaborate in the federation, where actually you just see one big pool of data and you don't care about where the data actually sit. You just let the federation find out how to do this distributed data fusion. Think about how is that distributed data fusion done today. Then we realize, okay, that simplifies the whole effort and the whole task. So that is federation. And that is actually what is used in the EarthServer Datacube Federation, where, as I said, autonomous data centers come together. The westernmost is currently sitting in Oregon in the US. It's the IEEE server. The easternmost is sitting in Taiwan. You see a screenshot here. And between that, we have a lot data centers contributing different data from satellite images to weather data to other thematic data. By the way, as this workshop is also about matchmaking, about meeting and finding new collaboration opportunities, let me mention that this federation, which currently offers already more than 160 petabyte of data, it is open and free to join. There is no cost for the data centers, for the data providers. It's transparent and democratic. We are currently finalizing a charter of EarthServer. We have both free and commercial data, and now you don't need to offer everything. You can offer just part of the Datacubes to the public. And so if you have data offerings, just contact me and join this federation. Okay, here is something special that I believe is also of interest to the ocean scientists. That is a particular functionality. Now that we have seen Datacubes and federations, and that is something which I actually would like to show again if I find the right. Here it is. Okay. We are looking into an aviation scenario. We are jumping around the applications today because there is a broad range of it and we find interesting bits here and there. In the Cube4NSSEC project, we look into aviation safety and we actually harvest aviation relevant data from German Weather Service. We harvest these data whenever they are offered. These are forecast data. If you look down here, you'll find that this is in the future, October 21st. Yes, we get forecasts for 48 hours at a 1 hour resolution. So what you see here is forecast, but then we also keep the old time slices. And so we get a long time series of weather data with a temporal resolution of 1 hour. Okay, we have wind speed here, we have icing, we have temperature, we have tropopause, and we have turbulence, for example. This is just a selection for this particular project. Of course, it could be anything else. To the right, you see the list of layers that we show here. And at the bottom, with a time series indicator, with a time slider, you can see how they go into the past. Okay, that is not what I wanted to show you actually, but something else. Did we talk about 4-dimensional data? I just showed you 2D on a map and a particular time slice. With this juxtapose widget, I'm sure you have seen such a thing before, but what you can do here is not just pick time, but you also can pick altitude. So 1,000 feet versus 8,000 feet. So you can go down and compare with 3,000 feet. And now suddenly we are getting closer to something that could be relevant for oceanographers, comparing different depth layers. But this is still not what pilots want. Here is something, wait a moment, I'm cleaning up. Looks like on my desk already. So here we can determine a flight path. Let us say we fly over Europe now. And then we assume a particular speed, 500 knots airspeed, and particular altitudes, like in a normal flight. And then we can compute flight times. We can compute the distance of legs, of course. This is just standard geometry. But what you also can get is a corridor along the flight path, where my demo is fooling me currently. Sometimes it's too fast and sometimes too slow. And then actually the pilot can see the wind speed along the path at the time the aircraft will pass by. So today it's not my friend. Somebody said every demo that has not some hiccup is a fake. Okay. For this one, okay, finally, hooray, it's here, and we see the wind speed. By the way, this is a typical big data problem. You don't want to transport the data cubes into the cockpit. However, this time series here is about 1 to 2 kilobytes, and that is something that you can get into the cockpit, definitely. Okay, so this is just a particular functionality where I believe that is something that can be relevant for oceanographers. Also, of course, we can do vertical cuts, but hey, let's move on. The second part, actually, I would like to put under the flag of standards. I said already, standards are very important for us, and we also actively participate and shape Datacube standards. Our advantage is that we gain interoperability, which is very important, in particular if you do data management and analytics. You want to be able to feed many different clients, visualization systems, and very often, actually, we are not at the end with visualization, but somewhere in the middle of a processing chain. Okay. Wait a moment. This is just killing my sequence here. Because I want to move over to another presentation that is about the standards. So, okay, Different format. That is actually taken from a tutorial on standards, but I have shortened that to be focused for today. So you hear me enthusiastic about standards, but I also hear people saying, bah, standards, thus they just limit my creativity and I'm forced to do things I don't want to do. Okay. So you want to be more creative. You want to build yourself a bike like this, which is not standard off the shelf. Okay, great thing. This is a really beautiful bike, but do you really want to build your own engine? Can you do that in your garage? Do you really want to cook the rubber of your tires? Do you really want to build light bulbs, for example? I guess what you really want to do is you want to go into the next shop and find there your particular tools and your particular parts, and then build them together with those parts that you have crafted yourselves. So the chassis you likely would do yourself indeed. And if in one shop you don't find what you search for, then you go to the next shop. And you can be sure that this fits together and you can build your custom bike because of standards. Okay. So standards may sometimes hurt. Yes, I know that very well firsthand. But in the end, you get a lot of advantages if the standards are well crafted, of course. Okay, I want to talk first about the data structure for Datacubes. Actually, in standardization world, the concept underlying Datacubes is called a coverage. It's not my invention. I didn't come up with that name. It's called a coverage, which is like a field in physics. So actually, a coverage is not just data cubes. It's gridded data, yes, but it also includes point clouds and general meshes. You find an abstract definition of that clarifies concepts and terminology, which is OGC Abstract Topic 6, and that is there is also ISO 19123-1 and -1. And then we have concretizations, which really allow checking for interoperability. And here we have the coverage implementation schema, CIS, that has been developed in OGC and has been adopted actually by ISO as 19123-2. Okay, so if we look at that, you find some old stuff like rectified and referenceable grid coverage that were very, very early approaches, more than 20 years old. The yellow part with a multi-point, curve, surface, and solid coverages is not our topic today. These are the point clouds and meshes. At some time, we sat together and we came up with an extension, a new additional concept to CIS, and in version 1.1 we find the general grid coverage, which is exactly what data cubes are. So with the general grid coverage, you model data cubes, for example. If you look at that on an abstract UML perspective, then you see that it consists of three components. The domain set contains the coordinate information, so where do we find data? The range set contains the payload, the pixels or voxels, if you will. And the range type actually provides the semantics of what the range set means. This utilizes actually another OGC standard, sensor web enablement, because they have the same problem. They need to describe the semantics of sensor data. That means, by the way, we can seamlessly carry over from sensors into coverages. And then an additional bucket was necessary to keep metadata. And we got so many different requests that in the end we said, okay, wait a moment. We give you one big bag and you can literally put in anything you want. So you see in UML notation the any here. The coverage doesn't understand what these metadata are, but it duly carries them along. If you want to see that concretely, here you have coverage in GML. You see at the top the root element general grid coverage, and then you find a domain set, you find a range set, and you find a range type. Hooray. You don't like XML? Okay. Let me offer you curly braces instead, JSON. This is a sample coverage in JSON notation. Still not your kind of thing? Okay. Well, we can use RDF to embed coverages into the semantic web world. This will go on for about a kilometer. It's extremely verbose, but it is a coverage. So we have several formats that are standard. They are complete, they contain all the information. It's just that they're inefficient. So not scalable. You cannot put terabyte coverage into a printable file. That will not work. By the way, there are other structures around that have notion like there is JSON and coverage JSON. This just has hijacked the name, but it's not compatible. Okay, but not our concern. Our concern currently is we want to be efficient. We want to have binary encodings. Okay, so the standards working group has added GeoTIFF, NetCDF, and more formats, which also can carry coverages. However, as we all know, not necessarily all metadata. Now we are stuck because, of course, people want to have both. They want to be informationally complete and they want to be efficient. Okay, so we sat down again and came up with the idea of a multi-part format where there is a container format, which can be anything you like. It can be multi-part MIME, it can be zip, it can be geopackage. And this container has, first of all, a header, which has the canonical information in one of the printable formats, let's say. And then parts can be factored out into further files, and that can use any suitable format, in particular binary. So we have combined the best of both worlds, and we have something that can be carried along, that can be sent out, that can even do a few internal structurings like collections or tiling, for example. So this is where the structure now is defined. Okay. As we are in Europe, maybe we talk about Inspire a little bit, this infrastructure endeavor towards a spatial data, a common spatial data infrastructure in Europe. That is something we have worked together with a few colleagues, Jordi Escriu, who now is with the European Commission, and Kati Schleit from Datacubes. And in the end, a very simple definition came up. Actually, Inspire coverages can be dealt with by the OGC, Web Coverage Service, only the core, nothing else, no extra bells and whistles, except for the WCPS. Here it's again our four-letter word, Web Coverage Processing Service, plus specific metadata. And here we see a typical application of the metadata bag and the coverage, because this is exactly where the Inspire metadata go. So you put them into the metadata bag. This has become the official good practice as Inspire, as the European Commission calls it. And that actually I want to show to you because it allows us to briefly look into how that works, how coverages work. So we have some hands-on demos where some mapping agencies were kind enough to provide data to us. And I'm just looking into this part right now, land cover metadata, where we have a web coverage service request. We will look at that in detail later on. We just executed and we get a result. This is the hard way. We get it as XML. Fortunately, it's small. You find, for example, the domain set here. You find the range set. You find blah, blah. You find the range type. And you find the metadata. And inside the metadata, you find the land cover, grid, coverage, metadata, according to the official definition, as it is on the Inspire schemas. So that tells you really can put in anything you want, and that can be very helpful. We do that in a project right now, combining different metadata which are extracted by different tools and processed by those different tools, and they do not interfere with each other because they all have their individual compartment inside the metadata slot. Okay, coming back. So that is actually what we just saw. Sorry. Now let's move on. Oh, by the way, going back one. So if you want, just copy these URLs. If it's too fast, please speak up. Oh, yeah. Don't know whether you can, but I cannot see the chat currently. So I don't know that. But don't worry, you will get all those URLs if you cannot follow and type. I have uploaded that. I can tell this on this occasion. Where is it? Here. And this is what I put into the chat right now, because here you see the presentation uploaded already. I did that right before our meeting here. And now let me put that into the chat. Here we are. And so you get the link now. Good. So on this occasion, let me check whether you have any questions here so that we can take up and discuss that. I don't see questions right now. So let us proceed. Once again, these are open and freely accessible. They serve to illustrate how Datacubes work via the coverage standards. So in summary, a coverage can be regular and irregular grids, that is the Datacubes, point clouds and meshes, and CIS 1.1 version. And that is identical. Actually, 1. Our next work will be to update this CIS 1.1. You see, work never stops. Now we want to do a service with that. We know about the data. What can we do with that? The web coverage service actually is a modular suite of standards that allow you to extract, to manipulate, to combine such coverages. And the WCS core, which is mandatory to implement for every WCS, is actually very simple. Give me a coverage or give me a subset of it and give it to me in my favorite format. Period. That is all, actually. This subsetting is subdivided into trimming, which retains the dimension. So 2D subset from 2D coverage, 3D subset from 3D coverage, and slicing, which reduces the number of dimensions, like 2D slice from a 3D time series or 1D pixel history from a 3-dimensional time series. Extensions, like string of pearls, add optional functionality facets. You see part of the diagram here, which explains the big picture. You see lots of extensions. We don't need to go into that because we will look at WCS in passing anyway. Actually, you see 2 strings of pearls here. That actually means that this different functionality you can use in various protocol bindings. So you can use get KVP or post, or you can use SOAP. Well, not many people use SOAP today any longer, but the others are still used. Good. That is something that you can inspect here. We have, actually, I will use a slightly different URL. That is the standards.rasterman.com, which I put now into the chat as well. Okay. And coming back, this is actually a playground, we call it, a sandbox that you have built up to explain the standards. It uses Rasterman and has all sorts of different demos here. I'll come back to that in a minute. Let me go quickly down because we are still with WCS. Let's not forget that and go to the WCS console. So this actually gives us a very low level view, which is good for developers. You can check out the various request types that are present with the get capabilities, which is done here automatically. You get the list of coverage objects that are available. You can look at this also the hard way, once again, by seeing the XML response, but I believe we don't want that. Okay, and then we see not only the get capabilities request, but also describe coverage and a get coverage. And that is what I want to show you next. You can try it out yourself here, but I have something prepared. Come on, that shows you how it works. In the end, you know, this is get KVP, the key value pair notation, which runs best in my PowerPoint. So you have some URL, then you have a service indication, WCS version 2.0, and the request type here is get coverage. In the simplest case, you get the whole coverage in its native format as stored in the server. Well, if it's a terabyte, you maybe don't want that. You want to get part of it, and so we come to subsetting. Actually, you can easily distinguish that. The trimming always is 2 coordinates. So in longitude, we do a trimming between 100 and 120 degrees. In latitude, we do a trimming between 50 and 60 degrees. And along time, actually, we do a slicing. You can see that because there is only 1 coordinate at this particular point in time. So here we would get back something two-dimensional. That allows you to do data reduction and extraction. If you want to have a different format, okay, then say so. For example, if you want to get that 2D cutout as a TIFF image, and that is WCS Core. As simple as that. It is actually something that we can try again here. So this NIR coverage is small enough that we can really extract it, for example, as a PNG image and visualize that in the browser. I don't do it, but if you want, you can try it out later on. Okay, you may have heard about a new hype by OGC called OAPI. It used to stand for Open API, then they wanted to see it called OGC API. And that is an initiative that goes through a lot of different compartments, features, coverages, processes, maps, tiles, and so on. It is somewhat RESTful, not totally, and it uses YAML without going into the technological detail. They want to call it now API, an application programming interface. Now, early on, API was a word that was used inside one computer to call another function. Like, for example, calling a database with a query, sending a query or so. But now it is suddenly replacing the term web services, although it's still web requests in the end. Of course, we always use HTTP underneath. If you want to see specifically that for the coverages, I have put in the link for the OGC workspace, the GitHub workspace, and a demo that is based on Rasterman. Yes, we implement that too, just to follow and experiment. However, it's still so much in flux that, okay, we don't know when this will be finished. The functionality is pretty similar to WCS. Actually, they have gone harvesting and have copied functionality. It's just new syntax and conventions. However, there are some detailed deviations, and the devil is in the detail. Just one example. You sense already, I'm not totally convinced about it. Here is one example. If you want to retrieve as per the core of OEPR coverages, you can retrieve a coverage or a subset of it. But the server may decide that you get that in a different resolution, because it might be big data and the server decides, oops, it's too big. So you don't get the expected resolution, but you get something downscaled. The funny thing is the server doesn't tell you. So you don't know what you get actually. You can enforce that you get the original resolution by adding a parameter scale equals 1. However, for doing this, the server must implement the scaling extension. And if the scaling extension is not supported, then bad luck. Maybe this simple example illustrates a little bit why I'm not convinced about it. And anyway, it is in flux since how many? More than 7 years now? Let's see. Whereas the WCS part is proven, it's proven on petabyte data and in lots of functionalities and applications. However, I want to come back to what we have mentioned before. I told you about WCS, and one part of that actually is WCPS. It's one extension that allows actually to send queries. And this is what makes it very powerful and flexible. So let's have a look at that one. Get coverage just allows you to retrieve, to extract, but this one allows you actually to do analytics. As I said, it knows the semantics of space and time, and so, as we have seen before already, you can address in latitude, in longitude, in time and date, and the service will know that. And because it knows the semantics of space and time, it can also deal with regular and irregular grids. Here is an example. Rather than giving you some big introduction now, I'll give you the flavor of it. Let us say from 3 MODIS scenes M1 to 3, we want to get the difference between the red and the infrared band, and we want to get that in TIFF format. Then we would use the black part here, which first defines a variable that inspects M1, M2, M3 in turn. So it's like a loop. And in the return clause, we say what we want to get back. So red minus NIR is what the server computes for us. And then it is shipped as TIFF. So we will get back 3 TIFF images. If we don't want all of them, we can express a filter predicate. Like, for example, I want only those where infrared exceeds some threshold for at least 1 pixel. In this case, we would add a where clause, which says if there is at least one a pixel that fulfills NIR greater than 127, then we want to retain this $C, otherwise we just discard it. So all of that is executed in the server, and unwanted data don't even leave the server, making this very efficient in transport. I can tell you the syntax, yes, it's different from SQL. I mentioned SQL MDA earlier. One difference here in WCPS is it has a syntax that is close to XPath and XQuery, because that actually is what our metadata mostly are. We have lots and lots of XML metadata, and today there is an interest in JSON, which XPath can handle as well. So by using this syntax, it gives us the opportunity to integrate data and metadata search. The second difference to SQL MDA is the semantics of space and time, which I mentioned already. But the rest, the underlying mechanics, is the same. And actually, we use that because in our implementation in Rasterman, what we do is we translate incoming WCPS request with the help of some metadata into such SQL MDA requests, and that is what the engine ultimately understands and evaluates. Okay, here is an example of what we can do with it. We can try and play web map service. So here we actually do data fusion again, but it's called differently in GIS. You just overlay 4 thematic layers. You have an orthophoto, water lines, water areas, and a DEM. So the $P, the orthophoto, it used to be black and white at some time in the past. So we multiply that into color space with 111. That gives us an RGB. We overlay that with $WL, the water lines, and this is a binary layer, water or no water. We multiply that with a particular color, and the same thing we do with the water areas. It's another thematic layer that we multiply with a different color. Finally, the DEM. Here we do a classification, some traffic light coloring, where we say, if this $D is greater than 260, we return red. Otherwise, if it's above 262, we return green. Otherwise, if 264 is exceeded, we return blue. And everything else will return 0, which will be mapped to transparent. And what you see at the top right is a screenshot of such a query that combines those layers in a GIS method. Okay, so we can do analytics, we can do processing. Actually, can go up to something like Fourier transform and can do a lot of stuff there. This is something that, again, we can try out. And if we go just, oops, one step back, then actually, now it's time to look a little bit into the demos because they also give you underlying WCPS requests. You see, if you go with the mouse over it, then you can see WCPS requests. And internally here, we see some race of 2 different situations, which shows why processing in the server is a good thing. Actually, people told us, what? So you use a WCPS query language and you translate even into something else. But that will be so slow. So finally, we did a demo where we said, wait a moment. If you use something like WMTS, it does the most stupid thing, and people say services must be stupid to be fast. WMTS just gives you back images. Okay. On the left-hand side, we see RGB image, a false color image, actually, not RGB, that is stored on the server and served by Apache. So when this page is loaded, Apache is asked to please send us that image file. This is a little bit bigger than shown here. So it is scaled down in this demonstration just to show it. On the right-hand side, we have done on the server, we have imported that before into Rasterman, and now the query actually does an NDVI and a threshold on it, greater than 0.7, plus multiplication with 255 so that we can see it. And you know what you see here? It's faster. Why that? There was processing involved that should be slower. Actually, the processing is so fast with this green cubes approach in Rasterman that you don't notice it. But you notice something else, and that is data transport. On the left-hand side, you transport 3 times 8-bit per pixel, 24-bit. On the right-hand side, you transport 1 bit per pixel. Okay, a grayscale maybe. You see also that this compresses nicely. And so actually much less data are transported. And that is the main effect that you see here. You can try it out by providing different thresholds here. And then you can see what the time is. Actually, the lower the bandwidth, the larger the difference will get. Okay, too much to think of. Let's come back and do something for fun again. WebGL is a cool thing. Some of you may be gamers, and so WebGL tells a thing to you because the Unreal Engine and others, they use WebGL, and then it can do this for you in the web browser. So the terrain draping actually can be moved around. There's a trick which allows to feed that. If you take a PNG and put elevation into the alpha channel, into the transparency channel, then WebGL can use that for rendering height. And that's what we do here. So actually you find here in the alpha channel the DEM, and in the RGB channels you find Sentinel-2 data. And that has been fetched from the database. And by the way, it's data fusion, right? Combining two data sets. You don't believe me that this is really a database query that is done on the fly? Okay, so let's set some bands to 0. And I show you a sunset scenario where we only get the red band. So this is more or less fun, but it's one of the things that you can do here. I leave it to you to go through these demos if you want and check out. Underneath of all of that, we always find WCPS. Let me come back. Come on. Talking about WCPS, how do you send that actually? How do you send a request? Option 1 is via a web request. So HTTP or HTTPS, you have the URL here with a service endpoint. You tell that you want to execute WCS2 with a processing request. And with a query parameter, you provide your query text that you write. You need to escape that. Actually, that is something that can be done for you, for example, also in the command line. And then the query goes to the server executes it, and you get back the result. Curl is a utility that you can use for a send URL from the command line. And so you would send the service, and then you would send the data part here, and the file that comes back you want to store in a PNG file, in test.png. Okay, the encoding is done by the tool for you, so you don't need to worry about the blanks and all those special characters here. So that's a way to send that. You want to use Python? Okay. Actually, you also can use the same requests. There are several Jupyter notebooks available that show you that. And then you do your Python code. You define the query as a string. You can, of course, compose that from various ingredients. And then you send, say, a post request or a get request, and you get a result. With this result, you can work immediately. You can use it as a NumPy array. You can put it into X array and what not to work in the Python world. Similar things are possible in R. That is something that EURAC has done, EURAC Research Center in Italy. And if you want to see how that works, then look into the corresponding client, where you find, hooray, the Jupyter notebook. And then you can read a little bit of introduction. You have seen that image before, and then we get our hands dirty with building, for example, get coverage requests. So that's all illustrated here. Good. Now, you will find people that say, no, instead of WCPS, we want to offer Python. Let's think about that for a moment. So you set up a server, a big, powerful machine with a lot of data, and then anybody can upload Python code and your server runs it. I mean, really anybody can come. Would you sleep well at night? I guess not. And I tell you, I can write a denial of service attack in Python in 2 lines. So Python is maybe not the best option as an API, as a service interface. This is why query languages have been invented, by the way. In the 1960s, people used COBOL, and no, COBOL is not our database language today, but it is SQL. Same thing here with WCPS. Okay, there are several more things that could be discussed, but I just wanted to sketch why Python is not the best possible idea. Good. So we have something like a Swiss Army knife now for pixel analytics, and you actually can hide that behind some GUIs, behind third-party clients. And the server has the opportunity to do a lot of optimization, parallelization, and federation. Here, actually, I have listed some tasks plus solutions if you want to try it out yourself. So it doesn't make sense to do that right now and here to bother you. But you find everything here that you need. This is the service URL. It goes to standards.rasterman.com. Here is the part that you need to replace with a string. Depending on what you use for sending the query, you may have to escape some characters like blanks and quotes, or sometimes not, depending on your tool, as I said. And then you can go and drill into the Datacubes. Let's say from our average land temperature Datacube, we want to extract a single time slice. Then actually, we pick here our date, so January 2014. And we say nothing about X and Y, so we get the full extent of X and Y. Okay, CSV. Sorry, this is a copy-paste error. CSV is certainly not the best possible format for an image. Maybe it makes more sense for a time slice to pick, let's say, PNG. You could use TIFF as well, but okay, now it's PNG. If you want to extract a timeline history, then actually would indicate the particular slice point, latitude, longitude. And as you did not mention time, you get, well, everything along time. And that now would go well with CSV indeed. You can also do aggregation. So, you may want to know the minimum temperature in January 2014. Then you again pick the time slice and you get the minimum over the full geographic extent and see what was the lowest temperature. Here is a more complex task that involves polygon clipping, showing you that no, we are not bound to just bounding boxes and rectangular areas. You can have polygons. You also can have multi-polygons, by the way. And with the help of the clip function, you can restrict that. This example shows in passing that you can provide further information to the encode function, like, for example, no data, so null value information. But you can also pass color ramps, and you can set TIFF tags, so whatever comes to your mind here, depending on the format, obviously. Here, if you are through with that one, and you still want to try out more, then, as I said, in this standards.rasterman.com sandbox, you will find with the demos always indicated the underlying WCPS query that answers it. And you can grab those and you can pull that into the WCPS demo. That is this one here. Sorry. Demo PS. Okay. And here we have a sandbox where you can type a query. And in the upper window, you will see the result. And if you don't know what to type, here are some examples. I'm taking the on-the-fly coloring. Then you get your WCPS query. And this prefix here actually is not part of the language. This is a hint to the client here that the result is an image and it should be displayed as an image. We send that to the server and we get back the result. You could do a conversion, say Celsius to Kelvin. And now you see that we indicate diagram here because that is not an image that we get back, but actually what we retrieve now is a diagram. So this is just a property of the client here. It's very simple, as you see. You type in query, you get back results. Okay. This is actually the tasks that can be done, and there can be more. Let me briefly show, where is it? Ah, yes. Okay. Again, in the Federation, this might be of interest at some time, and that is the Copernicus archives. Actually, this is currently being revamped, and we are talking with T-Systems. We are looking at adjusting that. But Mundi is one of the existing 5 Copernicus services, and we provide the Datacube view on top of the data. Of course, you can always download the files, but we have some Datacube view which may be preferred. So we can take the Sentinel-2 data and get them, of course. Oh, now the sharing is in my way. You can go back in history and retrieve other time slices, or you can extend that because you want to have some better coverage. Then it looks like that, and you get the data loaded and overlaid according to this time point. You can also do that with Sentinel-1 data and Sentinel-3 data, for example. So here's a lot of data available. Why am I saying this? Because there are quite some data already available in the Federation. And so why should you download and store yourself? This way you can easily go and grab on the fly what you need without worrying about storing now Sentinel data of the Northern Atlantic to a large extent, because that is something that archives like CreoDias can do, etc. Where is it? So .eu. So here now comes the page of the Federation, and you can look at the members here. My internet connection is a little bit slow, and you can go and find them here with different stuff like maritime data by Alfred Wegener Institute, Copernicus data, Formosat data, Jülich Research Center has climate time series. Land support has land management. Okay, that is not exactly relevant for the ocean. I'm just mentioning that in passing. And then we have, for example, the IEEE service in the US, which I mentioned. And if I go to the service landing page, then I go to the Amazon service that is sitting in Oregon. Okay. So now that we have seen this one, actually, let me come back. And this is the finish of my presentation here. Let me come back to the central one. So the main concept I wanted to bring to your door is Datacubes. They just simplify wrangling with multidimensional data, so spatiotemporal data, and ocean data naturally are, of course, multidimensional, and therefore Datacubes really can be of help here. They can be treated efficiently in the server, and with a language like WCPS, you can easily express in 2 lines actually what you want to the server to do. So you get not data, but you get results, you get answers to your questions. I presented to you briefly Rasterman, a tool that specializes on management and analytics of Datacubes. It has a lot of techniques inside to make processing fast and to allow federation, but also green computing and one thing, security. And interestingly, the first ones who asked us about advanced security was not industry, but was scientists. They said, yes, we want to publish data, but not all data. So this had to be implemented as well. Finally, you find some links collected here. The sandbox we have used already heavily here. Then there is a coverage tutorial on EarthServer. Where I can learn more about coverages and about coverage processing. The base URL, of course, leads you to the Federation. Our research group, ELSIS, the Large Scale Scientific Information Systems Research Group, is here linked as well, where you can find over 200 publications on the topic. And finally, in OGC, I maintain a wiki that gives you information and background on the standardization of coverages in OGC and ISO. Okay, and with that, actually, I would like to stop here. And I'm again happy and grateful to the organizers that I could give this talk here. And I'm happy and grateful to you that you participated here. And I would like to see, maybe we have some questions, comments. So coming back and inviting the audience to come here and share your thoughts with us. Okay. Once again, you find the slides. I will correct a few typos that I realized only now, and I will upload a revised version, an improved version within the next 10 minutes after our meeting here. And then you find the slides, including all the links there. What I also would like to mention is, I believe that goes by itself, that we are very open, very interested to partner and to implement use cases. I need, here it is. Ha, now I found it. Thank you, Katharina, for the hint. How much flexibility these provide for Python and R. Does one have advantages over another between these two in WCPS? Actually, no. It is always the same principle. You establish a query in your program, and this query you send via a request, and you get back a result, period. So you send request, get result. This query normally will not be hardwired. You will want to grab, let us say, coordinates from a user interface. You may want to add some processing into the query. This is simple string processing, which is supported well by both languages. Actually, I know that there are two different communities, one of them favoring Python, one of them in love with R. So there is not one is better, but they are just established tools, and both can be used for accessing the data cubes. Okay, please feel free to add more questions now that I have the Q&A open here. I was going to say, if you have ideas about a collaboration where Datacubes could play a role, then please do contact me. I put my email address into the chat, and then we can discuss opportunities for all sorts of things, including, for example, European funded projects. And I'm just checking, okay. No further question currently. And I'll be happy to chat about that. Okay, so last call for further questions or comments, hints, whatever. Okay, if we have none, then once again, thank you very much for attending. And I wish you a nice evening or nice afternoon, whatever time zone you are in currently. Thank you for joining, and bye-bye, everybody.